they come in. So let me, okay, let's get started. I guess there are three things to cover today. I guess first one is finish the stuff from last time about the attribute disclosure risk, the computation. I think we have some unsolved. I mean, there are a few slides I think we need to go over, and also just open up for questions. I know it's not something very intuitive, especially some of the computing steps. So we can go through that and then answer any questions you might have. And then we're gonna take the time, I guess, for each of the project team to talk about what their synthesis model is. Especially, I think I asked for, if you can, using a few slides instead of like a long write-up and then scrolling up and down to show what you have done. So we'll spend some time doing that. And then the last part will be start talking about differential privacy. Okay, so that will be the plan for today. And to get us started, so the meeting, okay, let me share my slides from last time. I update the slide a little bit this morning to correct some typos. So if you're looking at the version that I uploaded on GitHub, it's slightly different from last time, but the overall general idea is still the same. Okay. All right. Okay. So we were here. I think we talked about this. I think we're on this example, if I remember correctly. I think we were here. Okay, all right. Let me maybe start from here. Okay. So so we're on the CE data set, okay? And we have, we're trying to do a attribute disclosure risk evaluation, okay? And in particular, we're looking at our YIS, which is the guess, I should say is the random variable. The YIS, this thing, is the random variable that the intruder is using to represent the uncertainty of the guess of the possible values for the ith observation, the synthesized, in this case, the log income. Okay. Now, Y star is any particular guess the intruder has, right? So by Bayes' rule, we know that it is the product proportional to the product of what if the guess Y star is indeed the value, what is the probability that you will generate your synthetic data, and then what is the prior that you have for a particular Y star when you are guessing it. And in particular, we know that we use a uniform prior for this. So the key becomes how to compute this particular probability, okay? And we know that Z is the synthetic data. And in our demo, this is a simple copy, right? Single copy of the CE sample. And we save it as in CE data syn, okay? YUS is the unsynthesized variables. So it contains rural area, urban rural status, race, and expenditure in the CE sample. So the difficulty part, I guess, the difficult part here is, so first of all, we assume the worst case scenario. So A, which is the auxiliary information that the intruder knows, is what we call the worst case scenario, that if I'm trying to evaluate the risk, the attributed risk for observation we assume that the intruder knows every other record in the synthesized data, okay? And we also assume that the intruder knows that the synthesis model is a simple linear regression model, okay? And we assume a uniform prior, so in the end, we are focused on equation 9, okay? And equation 9, as we know, that the only difference between, let me just go to the slide. The only difference really between equation 9 and what we actually fit the model is about the difference of this thing, right? So if you look at, so this part was equation 9, except now we have the parameters in the model, like in here as well. And the only difference really is that now we have a particular guess of YIS, okay? And we guess it as Y star. Whereas when we fit the model, if you remember this, that's the posterior, if you remember, for that we have fit, and we actually use this posterior, the parameter draws from its posterior, and then we do the posterior predicted distribution to get the synthetic data. Okay, so the key difference is about the y, and in particular about YIS. Okay, and in one case is y star, which is the guess that we're trying to estimate. In another case will just be yi, which will be the actual true value of it. Okay, so it is because of this we're using the importance sampling technique. Okay, oops, and I think we are here last time. Okay, so the importance sampling strategy we know is that we are trying to estimate the expectation of g theta with respect to an unknown distribution f. Okay, and the unknown distribution f might not be easy to get, but we have a convenient f star distribution that can be used as proposal distribution, and it is this ratio. You can think of this as weights, right? So we estimate the ratio of f over f star given the particular h, theta h parameter draws that you're having, and then you get the ratio across. This is renormalization in some way, and then you're able to use importance sampling to estimate the expectation of the g theta. Okay, so g theta is that equation 9, which now I use equation 11. So this is our goal. We're trying to get a good estimation of this, expectation of this. And f theta is the distribution, almost like a posterior distribution of theta given the particular y star that you guessed. And then the f star, which is what we call the convenient distribution, will just be the posterior distribution that we actually have estimated already when we're doing the synthetic data generation. Okay, so it is all of these pieces being put together in order to do the calculation. So the importance sampling strategy for g theta h is, we know, is this particular one, given that you have your draws of theta h. And we know that, well, the model, the regression model that we have was what? Yi is independent, right? Normal with mean, I guess, beta 0 plus beta 1 times xi, and then sigma, right? So this is our final synthesis model that we used, right? So for a particular set of theta, in this case, the parameters, they're the beta 0, beta 1, and then sigma, right? So for particular h, you can plug in that, and then xi is the log expenditure, which is unsynthesized and given. So you are able to express your g theta h by making the product, right? Taking the product of all of the normal PDF evaluated at those points. Okay, so don't forget the yi tilde. It is the synthesized synthetic log income for observation I, and xi is the unsynthesized log income. Okay, so we can now, because of the model, the Bayesian, simple Bayesian linear regression model that we used, we can now express the regular equation 14 on the first line to the second that is very specific to the model that we're working with. Okay, so I think Isaac at some point earlier asked about when you're doing this particular exercise, which model should we use? So the demonstration I'm using here is based on the model that we fit. I should say I fit, I guess, as a demo in class, that I only fit a simple linear regression model for the log income given the log expenditure. So that's the model that I use, right? So I have beta 0, beta 1, and sigma. But also earlier this semester, we all fitted a multiple linear regression, I think. Depends on which predictors you use, because we have two others, right? The urban rural as well as the race category of the reference person. So if you're using that as in your S, remember S is the information about the model that the intruder will know. Then for you, if you're using a multiple linear regression, then your model here will be different from what I do here. And that means your equation 14 will be slightly different as well. Okay, so keep that in mind. And this is also important later on as you're going to be doing your project. And if you want to, well, I should say that now everybody sees how complicated the whole process is. So I'm not sure if anybody is really going to evaluate attribute disclosure for your project, but if you want to, this is the way to move forward, okay? And then that will be directly related to what kind of model you're fitting, and then that will be how your G theta H become, okay? So it's gonna be very model specific, and I'm using this as example to show how things can be done, okay? So, all right, and then about the ratio, right? About the particular, I think this is where we are last time. The ratio in particular, we know that it's about F theta H divided by F star theta H, right? And that's on the top, and then in the bottom will be like summing over. That's how you were using that proposal distribution H from 1 to capital H, and then this particular ratio, okay? So last time we were here, we're trying to explain how you can do it in practice. So what this is, as you can see that I'm just using pH to represent the G theta H function, okay? And then the QH, it is this particular ratio that I'm trying to compute, okay? This is just a different way to write it so I can fit everything on the same slide. And so for GH, the G theta H, we just did it on the previous slide. And you notice that here, because it's estimating this, right? It's estimating the probability of getting the synthetic data. So the Y that you're supplying is the synthetic value, okay? Whereas now if we move to QH, which is F theta, like on the top here, is the F theta H over the F star theta H. So when that happens, remember that because F theta H, so remember F is the inconvenient, I shouldn't say, like not familiar data density that you're working with. And in that case, it is the guess that you're trying to estimate, right? Whereas for the F star theta H, we know that for that Y, it will just coming from directly from the data, okay? Because what we remember, if you remember F theta and F star theta based on our definition, it is just this, right? Because that's the convenient distribution, and that is the model that we have estimated from the model, and then we used it for synthesizing the synthetic data. Whereas the F theta, we know it's the distribution of theta given the particular YIS is Y star, right? Because we're changing that particular guess. And then everything else, I think, will just be your Y, YI, negative YS, and then YUS, I think, and then A and S over here, right? So it is because we defined this two early on. So when we're trying to compute the ratio of this two, the first one will just be about your guess. So that's why your Y star, I mean, your Y is Y star in your normal PDF. And then your, for the second term, for F star, your Y is the actual value because that corresponds to how you fit this model, okay? So a lot of pieces going on, and that's how you can finally determine how you're able to calculate your pH and QH. And then of course, it's a lot of involved steps in the end to perform this computation. Okay? But we spend the time talking about this. I mean, for one thing is I want you to get to know the general strategy of doing things. And, but also, of course, if you later are going to do this for your project, this will be a good starting point for you to move forward. Okay. So I hope almost everybody had gone through this because I asked you to do a summary doing all of the computation later for the entire data set, because in the slides, what I included is only for a couple of observations to do the demo. So I'm gonna move on doing that to show you what you could do, and then we can hear from some of you. I will do a breakout room first so you can share with each other what you have computed and see if you get the same results. And then we come back to talk about it as a whole group. Okay, so here, as you can see, when you calculate, so we're doing this for the C sample, okay? And in particular, there are certain things that I've done for this, and you can choose otherwise. But for the ease of computation later, so we first of all have to take the log, because all of the model was fit on the log scale. So we have to work with the log expenditure and log income. So that's why we did that. But also later on, you will see that just to give a sense of like what are the possible Y star that we can take. I round all of the logged value with 1 decimal point, just because later I can show you, well, if I have the true value to be like say 10.5, then I have maybe the other ones that will be my possible guesses will just be around that 10.5. And then when you take the log, you can have many decimal points. For me, just for ease of computation, like I said, we round the numbers, round the logged values to 1 decimal point here. Okay. So for illustration purpose, I chose the 8th CU, which has the true income, log income 11.6. Remember, I rounded, so we only have 1 decimal point there. And the synthesized value for that record is 10.1, okay? And then the X1, or XI in this case, it is the log expenditure, okay? So we need the X here because, as we can see in the detailed computation here that we have just shown you, when you are applying that PDF, normal PDF, you need the XI as well. Okay, so we need those pieces all together to do the computation. Okay, all right. So so I was doing something simple, as you can see that I chose the 8th record, and I get the YI from the original data that's given, and then I started off with 11 guesses, including the true value 11.6, but I also just did like with the increment of -0.5 for 5 records, and then with increment of +0.5 with 5 records. Okay, so I came up with a collection of 11 possible guesses, and I used a uniform prior for that, as you remember. So the 1/11, it's going to be a constant, and then later on, it's just going to be going to the proportional sign. Okay. But again, this is assuming a collection of 11 possible guesses. You can do more, you can do less, and you don't have to go with like a fixed increment like what I'm doing. In short, you probably just want to consider those possible guesses that you think really are possible, in the sense that it's in the neighborhood and that is reasonable to make the assumption. So this will be a starting point. Okay, and if you're working with categorical data, as you can see, I mean, not in our case, but if you go back to the ACS data, for example, say if I'm working with the marital status variable, and then if the true value is 1, and it has only 6 levels, what you can do is the possible guess, right? The possible guesses for that variable will just be all of the 6 possible values. So that will be a way to do the neighborhood type of computation if you are working with categorical data. Okay, for numerical data, as you can see here, I'm doing some kind of a proxy, in the sense that I rounded first, so I only need to sort of worry about 1 decimal point, so I don't have like that many to think about. And also I chose 0.5, arbitrary, to be honest, the increment, and you can choose smaller, you can choose larger, and you don't have to choose, like I said, a fixed increment. You can all of a sudden change with 0.7 or things like that. Okay, so this is just a demonstration. And we know that theta is the parameters, right, from the simple linear regression that we have fit. And we know that we should use a large enough number of draws from theta to do the important sampling estimation. So I chose 50, okay? But you can choose other numbers, like 100 or 200. I mean, the short story is, if you look at what we do here, the larger the number, the value of capital H, the more computation you have to do, okay? And the smaller it is, the less. But of course, the larger the H, the better the approximation, right? So there's a trade-off. I chose 50 because overall I think it will be a good enough approximation. But if you choose like 100 or 200, it would just be an even better approximation, but it would just probably take a little bit longer to do. Okay, so really depends, because think about the dimension here. H is how many draws from the model that you're trying to use to do your approximation. But there's another dimension that is how many, actually many dimensions, I should say. Another way to consider how many draws you want to use is, again, you are, let's say, I chose like a collection of 11 possible guesses, right? So that means, well, I have to do it for 11 times at least. And so if you are choosing a larger size collection of possible guesses, then you might want to maybe reduce your capital H, because all of them come together to determine how much computing power or resources you need. So that is another consideration. And one last consideration is in the demo here on the slide, for example, I did a CU8, right? And then I guess I think I did another CU number 10, just as a comparison. But in practice, you want to do this kind of attribute disclosure computation for all of your observations and then get a summary from there. So how large your data set is another consideration of how much you want to do, okay? So how large the collection for each record that you're comparing to. That's the number of Y stars that you have for each YI. And then the other thing is how many observations you're computing your attribute disclosure risk for. That's another thing. And then the last thing is, well, what we were talking about here, how many parameter draws for the important sampling strategy that you want to use. Okay, so you can experiment. But I just want to say that all of this contribute to how much computing time you will need to get things started. All right, so one slight little thing here I want to add, and I think maybe some of you have seen this before, is, well, if you recall what pH is, we are taking the product of a bunch of PDF of normal, okay? It's gonna be very small when and we have what, 994 observations, I think, in this data set for the CE data. So when you're taking product of a bunch of PDF, in this case, I think they're all small. So you're gonna start to get like very small number, and then the computing stability gonna be gone, in a sense that your pH, if you don't do anything about it, pH at some point is just gonna be 0. Like R gonna record it as 0. So it's gonna be problematic if you want to compute it. So I'm introducing you to this log sum log sum exponential function here. And actually, before we move on and then talking about it, maybe I would just use a breakout room so you all can discuss with people in your breakout room to get a sense of what this is trying to do. And again, equation 15 here, you can prove that this is true. And then the code that I put it down there is directly doing equation 15. Okay, so left-hand side is what we want to get. Right-hand side is a way to get around it, because, well, the computing cannot be stable once you're multiplying a lot of normal PDFs, and then you get something super small that R will just take it as 0. Okay, so I'm gonna recording, and yeah, Kevin, go ahead with your question.
Reese, if you wanted to ask, it was Reese's question.
Oh yeah, Reese, do you want?
Sure. So, do you mind just going back to that slide?
Sure. It's the computation, right? Yeah, here.
Yeah. So, like, I was not sure how we got from the pH equation to equation 15, because, like, I think like equation 15 is log pH times QH, right?
Mm-hmm.
And like,
Oh, I see.
I'm just not sure why pH times QH is like the summation of exponent.
Yeah.
Exponent
Okay.
right?
Good point. Yeah. So great question. And I think I usually include, I guess, all of the steps. Okay. So just so you know, what we're trying to do is this. Okay, we're trying to get the expectation of pH. It's pH and QH, okay? And this is the thing that we're trying to compute, okay? what I was suggesting us to look into this is that, well, we know the pH form. So QH is the ratio thing that you have to do, and then take the sum, or I mean, the ratio of F over F star, and then you do that for all of the different H's, right? And then in the denominator, you sum them up. But pH will become a problem because pH, we know it's this form, and this form can be really small later because remember, we're multiplying a bunch of small values, and then, well, if you multiply 0.1 to 1,000 times, you're going to get something really tiny, right? So in R, it's just going to become 0. So what I was suggesting is, well, in the end, we want this, right? That means in the end, we want pH times QH. And then we take the sum and all that, but let's not worry about it. So because pH is going to be really small, I'm suggesting us to take the log of this whole thing, okay? Because we'll be more stable. And what we're doing, as you will see soon, well, I will use the breakout room again, I guess now, because the question is being asked, and then we can get the time to do the explanation. That notice this particular trick is trying to get this, okay? And what we're trying to do is pH is really small. So, and then, I mean, QH will be, well, it's also, QH actually also is between 0 and 1. So just one more term that you're actually like multiplying with it together. So when you have really small values like this, what people usually do would take the log and work on the log scale. Okay? But in the end, what we still want is this thing. Okay? So, I shouldn't, yeah, I didn't mean that pH will directly become equation 15, okay? I meant that, well, pH is really small, and our goal is to get the sum of pH times QH. So equation 15 is a way out to help us to still keep the computing feasible, okay? So I guess with that in mind, maybe we spend, I guess, 2 more minutes to go back to your breakout room. Let me do that. All right. Any further comments or questions, like whether now equation 15, as well as what we do later on with the code below and what we're doing? Any comments, questions? Does it make sense now? Reese, I don't want to pick up on you, but is it making sense? Better sense now?
Yeah, it is making sense now.
Okay. Yeah. So right. So next round I probably will make the slide slightly different. Like here, we're trying to get the log. Well, because pH times QH is too small, so we're working on the log. So later you will see that all of the computation once we're done is about the log. So it's not about. Yeah. What we're doing. So what we're doing here is not computing this probability. I think earlier, I think the screen froze. Okay, so this slide is trying to say that, well, this is going to be too small, because when we do PZ given YI S equals to Y star, YUS, A and S, this will be too small because of pH going to be too small. So we're taking the log of this whole thing and trying to figure out how to do the computation later. Okay, so you will see that for the next few slides, we're getting log of this probability, and it's still going to be very, like, some very large negative number if you have done the computation. But what we're trying to show you here using equation 15 is actually a very commonly used trick. Okay, if you are trying to keep the stability of the computing, and then make sure that you can get log of the sum of the EXP. What you're doing is you take the maximum, which we define as A, okay, of the XI. And by the way, in the setup that I wrote here, XI is a, I think is a vector of, it's a log vector, okay? And what we're doing is, well, if you look at this, if Xi is a log vector, we take the expectation of it. So each element now is becoming its original scale and then take the sum. That's what we actually was hoping to do, right? Because this was being approximated, I should say, by doing PH and QH over here, okay? So we want this, and we took the log of this, okay? So that is the log vector that we're going to supply into, the compute log sum exp function. And then the xi is the vector, is a log vector. And then what we do is we find its maximum, subtract it from each observation of the vector, take the explanation, and then you do the regular thing, but then don't forget that you add back the maximum. Okay, so pretty much it's done very quickly, and the code, the little function that I wrote below, is directly translating equation 15. Okay. All right, so here keep in mind that we're getting the logged probability because the original scale of the probability is too small, so we cannot handle it. And then the next part, it's a little bit tedious. I probably wouldn't go through the code in detail in class. But what we're trying to do here is that, remember, we have a collection of guesses. So I named G as the collection. I mean, the number of guesses in our collection. So we're looping through that because we have to compute the situation for each Y star. Okay. So that's the outer loop that I wrote here. And then for each of that, we compute the QH, okay, and then the PH, QH, and all that. So, and then I multiply the PH and QH because that's what we, sorry, let me rewrite this. The form, if you remember, is we have QH, we have PH, and we're taking the log, okay, and H, of course, is one of the loops that you have to do, okay, so this is the loop over here that you see, okay? Looping over all of the possible edges. And the code, the actual code, like you see that we're using dnorm everywhere because that's the normal density evaluation that we have figured out early on how we can do it. And I took the log every time just because now we are working on the log scale. Okay, so there was some detail in the code itself. Overall, it should work. And in the end, we get the log of pH as a vector, okay, like a vector of length capital H. And then in the end, I use this compute log sum exp function just to convert it into the log scale, okay? And I name it as log z, and that is the log of the pz given yis equals to y star, yus, a, and s, okay? But of course, this is for each different observation, each different guesses. So we will have to record that as a vector of, for now you have a vector length of capital G, and that collects all of the log Z that you computed based on all of the H's that you have done. And then for each of one of the capital G number of guesses that you have. Okay, so it's a little bit tedious, a lot of things going on, but it is, I think, overall good practice for you to go through this. And so we put a uniform prior, right? So the log PZ would just be proportional to log this, right? And I mean, that's what we just did over there. And so what we have eventually, as you know, is that we have G number of guesses, okay? Okay. And then for each of them, we have a logged probability, okay? So at the end, well, we're going to use this log sum exp trick again because we not only just want to work on the log scale, we want to rank or compute the p probability of each of the guesses. Okay, so what I was trying to say is we have the logged probability for each of the guesses. We have 11 guesses in our example. Okay, so we have the logged probability, but what we want is the probability of each of the cases, not the logged. So you will have to do something similar to what the equation 15, that trick, did before. So I won't go into detail, but you can see something very similar, that we get the maximum, we subtract it from all of the elements of the vector, and then take the expectation and all that, okay? But in the end, once I have done this, you will see that I have a outcome. And let me actually just show you the outcome for the particular CU8, okay? So in for CU8, what I did once I did all of that is I sort it. Okay, I sort the probability from the largest to the smallest, and I have 11 guesses. Okay, so the index, the first column here, I think just goes with the index of the order of the original, like the sequence of the guesses. And but then we sort by probability, so you can see that the most likely guess among the 11 guesses is 12.6, and it has a renormalized probability of 0.0923. Okay, it's the highest, and the lowest is 9.1, which has the probability of 0.0878. Okay? And for our truth, this relates to the rank that I will mention in a minute. I think our truth is 11.6, right? Yeah. The true value, we chose it as one of the guesses, right? So you can find its probability, like that will be the attribute disclosure probability, guessing it correctly. And you can also know the rank. In this case, is rank number 4 out of 11 guesses that you have proposed. So this is a way to compute your attribute disclosure. And I did another one with CU number 10, which actually has the same outcome, the true outcome, the true income, I would say log income, but with a different synthesized value, and then of course a different log expenditure. It's still also ranked as number 4, actually, among its neighborhood of 11 guesses, including itself, but the probability seems to be slightly different. Okay? So many things going on here, as you can see, and what I want to mention is, well, yeah, if I come back, I think I have one more slides here, yeah. So typically you will repeat this for every observation in your data set, and you probably want to write a function to do that. And a couple of things I want to mention is that notice that in the example that I did, we specifically chose 11 possible guesses, okay? You can expand that collection, you can shrink that collection whichever way you want. But this particular setup that I use is, well, really just to make our life a little bit easier, because you can't have actually infinite number of possible guesses that you want to do, right? I chose 11, and in particular, it's not about the number 11, it's more about like the possible values that I guess will be reasonable to be guessed. So that's how I came up with this 11 possible guesses, and then I chose the 0.5 or negative 0.5 increment going either way as possible proposed guesses here. One thing people could argue that why doing this is sufficient is because, say, I consider 11 possible guesses, right? And among the 11 possible guesses, let's come back maybe to this example, to the CU10 over here. Among the 11 guesses, the truth is being ranked number 4, okay? And then if the 11 guesses are splitting probability 1 of being guessed correctly, then for my particular guess of the truth, it has a assigned 0.092 probability being guessed correctly, okay? So it is conservative to some degree that imagine if now I expand my collection of 11 guesses to 20, right? Then this number could only drop, right? It can never increase, okay? And also the rank, number 4, could only be dropping as well, because now if I start to consider other possible guesses, then the one that I have right now, number 4, being ranked number 4, as well as the probability of 0.092 could only be decreasing more, okay? So that's one reason, if you only try a small collection, you should still be fine if you think your results are good enough. But let's say if instead of 11, you do 5, and then you realize that my truth is always ranked number 1, right? So that might be a thing that you might want to adjust how you're evaluating the risks, okay? So 11 is, I mean, again, it's arbitrary. I picked it just for as an example. But you can play with other cases if you want. And typically in the end, you can summarize and visualize the distributions of the probability and rank. And I think I probably asked you all to do it. So instead of asking volunteer to show their screen. Maybe I will just create a new, let me see, create a new set of breakout rooms so you can have a small discussion first, and then I can show my results to you all. I mean, I did a quick run of all of the results, of all of the observations, but welcome anybody else who wants to share. Okay, so let me.
I don't think we can hear you.
Oh, I just realized I muted myself. Never mind. Thank you for letting me know. I've been talking to myself for a little bit. All right, sorry. I was saying, anybody wants to share what they have found out? Now I feel better because then I might hear a response instead of me awkwardly talking to myself about what I have found. Anyone? Well, no response is okay. What I was saying is if you are trying to, yeah, so the function that I provided is only for a particular CU, right? And if you want to run this for all of the observation, you might just like wrap everything together and then doing, I guess, like a bigger loop, looping through all of the observation. And then each iteration looping through the observations, you want to, I guess, record the probability that the truth will be identified correctly, right? And then the other one may be the rank that it is being ranked among, like say in my case, the 11 possible guesses. So let me actually just show you what I did just to show you, well, the outcome. But what I did really was just writing everything in a big function and then go from there, right? So I return, first of all, the probability of the true value being guessed correctly. And this is, yeah, so I was using the same 11, like a collection of 11 possible guesses for each of the 994 observations. And I got this, you know, across the 11 guesses, the renormalized probability of the true value being guessed correctly. So, well, it's not that surprising. I mean, you can see, I mean, earlier with CU8 and CU10, we see that the 11 guesses, I mean, they probably are not that much different from each other, and it's 11 in total, so it's not that different, I guess, from 1 divided by 11. Let me just see. Yeah, so in some way, well, all of the computation that we did is not that far from the prior that we chose, you know what I mean? But still, I mean, the computation should be done correctly because we're defining the probability in the way that we did, and then we have to perform the computation accordingly. You can see that like you can do a histogram of doing like counting, in this case, the frequency of all of the counts of the attribute disclosure risk for in terms of probability of the true value. And I also recorded the rank of the true value being guessed correctly. So in the CU8 and CU10 example that we saw, we have, I think both of them are being number 4. And so you can see that if I do this for all of the observations, you will have, I think at most, well, you will have some records being identified as the top one, okay? But very few. A majority of them are number 7, okay, as you can see. And then nothing more than, I mean, nothing ranked even further from that. Note that we have 11 possible guesses for each observation. So the maximum it will be 11, ranked as the 11th. But this is the results that I got. And anybody, any comments or addition to what you have done, or if you tried a different, maybe a different collection of records or a different model that you fit for the model, anything you want to share before we move on to talk about your projects would be good. Let me get Maggie first.
Oh, so I'm just wondering if say I wrote a function, but then the main codes are the same, would I get different answers, like different rank or probability from yours? Because I did get different ones.
Yeah, good point. Okay, so I was thinking about that the other day as well. And So Maggie's question is, if we are using exactly the same, like if you're using my code, but just like wrap it up, right? Like going through all of the observations. Say for CU8 and CU10, would you get a different number, or the normalized probability will always be the one that I shared and the rank wouldn't change? Yeah, Sarah?
I know for me it's different, but that's also because my model is different than yours. So I'm just like that created, and I'm not setting. I can't figure out how to set C correctly anyway. But yeah, so my model is different than yours, so the value it's fitting is just different. Yeah.
Yeah, so if the models are different, then all of the thetas will be different, for sure. Okay, so that might be what it was. I mean, for Sarah, I'm sure it will be different because they yeah, she fit a different model. Maggie, did you fit the same model as I did? Yeah, you have to unmute.
Yes, I think I did.
Okay.
But then I tried for a sequence of different lengths. I tried it for like 21 guesses in a sequence, and they also return different ranks.
I see. Okay. Interesting. Yeah. So I guess what I can say is, if it's a different model, then of course you will get something different. Like when we say different model, I guess, Sarah, you mean like you fit a like, say, multiple linear regression to the model, right? To the data. So that will certainly be different. And I should mention, let's see, the one that I did, I think, did I set seed in the? Because the thing is, the H, like I chose H to be 50, right? So I got the first 50 rows of the parameter draws from my post. And I will probably have to go back to look if I set seed correctly for doing the Bayesian model estimation. Because if you do something different from me, then your H, like all of the parameter draws for beta 0, beta 1, and sigma will be different from mine. And that will result something, I think, different. Like, are your results like quite different from mine, or like they're in the ballpark?
So my ranks are not exactly the same, but the probabilities are very similar. They are not the same, but they're very similar. And like they don't, so say if ranking from 1 to 11, they do have different ranks, but they don't differ that much in probability.
I see. Yeah. So right. So I mean, if I think about it, I think if we have exactly the same model and then exactly the same parameter draws that we fit in, I don't think there should be a difference, because I think beyond that, nothing is random, right? Because everything is sort of deterministic when we compute it, unless I already closed the slides, but you know what I mean. Like, say, once we fit in the same theta, and then right, because basically all of the function that we did, nothing. I don't think we don't, right? We estimate. I mean, we evaluate under the d norm, take the log, take the sum, and then doing all of the things that we did. I think nothing is random. So if we use exactly the same, then it should be the same. But if you have a different model, or if you have different parameter draw numbers, then that will be different. Okay. Mm-hmm. Isaac, did you have another question that you were trying to say? Mm-hmm.
Yeah, I just noticed the code that was like in the slides. I changed the name from post to posterior. Let me share here.
Mm-hmm. Sure. I have to make you able to share. Give me a second. I have this weird thing these days that I. Okay. You should be able to share now. Oh no, never mind. I clicked. Oh yeah, I did it.
It's allowing me.
Yeah. So
the in selecting 1 through H here, like, is there a reason we take the first 50 of our draws?
No
okay.
Reason. Yeah. So good point. Good catch. So I think no reason for me, and this is very similar to like from which are the parameters that we should use to synthesize our data. I chose like the first 20 or something, but you can always, they're all converged. So I think anything is fine, and they're independent from each other as long as you do the thinning. So, but then because of the different choices that you make, like from different iterations, then the results might be slightly different.
Okay, I didn't know if it was like a rigid, like the very first is like a.
No, it doesn't
Okay.
have to be. Yeah, so that's a good question. I mean, because if you go back to how we design the importance sampling, we are trying to use the F star as the proposal distribution, right? And the proposal distribution is it's the posterior distribution pretty much, like we fit the model for. So as long as you're using draws from that distribution, you can use like 50, you can use 500, and whether you want to use the first 50 or the last 50, it's all fine. They're all doing some kind of approximation, and they should not be that different in the end in terms of the results.
That's what I figured. I just wanted to
Sure.
clarify. Stood out to me.
I mean, it's a great question. And I think Maggie's comment earlier is also definitely relevant. And yeah, so if I try to remember what we did, I think when we're doing the, let's see. Yeah, when the attribute, let's see, the identification disclosure, I think like for the utility evaluation and attribute disclosure now, as well as the identification disclosure, I think probably nothing really is rendered in the process. I mean, if I think back, I mean, the model fitting, which is in the Bayesian synthesis model lectures, I mean, there are some variability, of course. And then, of course, when you're generating your synthetic data, you might get something different from mine. And or like anybody else's if you do that. But then if we're using the same draws, the same synthetic data that we evaluate, I think, yeah, especially remember a few weeks back, I guess, for the attribute, for the identification disclosure, the 3 summaries that I asked you to do, and we compare results and all that. I think in the end, like I definitely remember one time that we're comparing the results, we should get exactly the same thing. That if I remember I gave you like 3 different synthetic data sets and asked you to take the average. Once you do all of that there's no random thing there, okay? But overall, I think this is a good thing to keep in mind because, well, compare results and make sure they're doing right. That's always an important step. Okay. Any other comments? Questions? Okay, if not, let me stop.